Hi everyone, this is TinyML team from Data Analytics and Intelligence Lab, DAMO Academy, Alibaba Group. Here is an introduction to our latest work, a fast, accurate, and efficient object detection framework, DAMO-YOLO. This is our development team of DAMO-YOLO from TinyML team. Our research interests include object detection, model quantization, and neural architecture search, which is also known as NAS. We are recruiting research interns, so if you have any issues or questions on DAMO-YOLO, or if you are very interested in object detection, quantization, or NAS, please contact us directly by scanning the QR codes in the lower left corner of this page. This introduction includes 5 sections. First, we will introduce the object detection task briefly, to help those who are fresh in this area to know the basic task definition and application scenarios. Then we will make a simple overview of recent projects on object detection and analyze the design motivation and advantages of DAMO-YOLO. Finally, we will make a comprehensive analysis of the technology value, application value, and implementation of DAMO-YOLO to help you understand and apply DAMO-YOLO to your tasks better. The goal or the definition of object detection is to locate objects of interest with their positions and sizes in images or spaces. In general, its inputs could be images, videos, or point clouds, and its outputs could be the categories and bounding boxes of objects. The figure on the left is an example of object detection. After inputting such an image, it outputs the categories, positions, and sizes of objects of interest, where positions and sizes are represented by detected bounding boxes. The application scenarios are diverse. For example, we need to detect cars and pedestrians in autopilot scenario. We need to detect budgies in harbor management systems using object detection methods. These are examples of direct application of object detection. Besides, it's a fundamental task in many industrial computer vision applications. For instance, both intrusion detection and popular face recognition are based on pedestrian and face detection. We can see that object detection is widely used in our daily life and is important to some CV applications. Therefore, it's a competitive research field. For now, there are various kinds of object detection frameworks in public. Here we categorize them into a few types according to their characteristics and users. On the one hand, both MMDT by SenseTime and Paddle detection by Baidu belong to the large and complete framework. They follow the latest algorithms in academia and contain hundreds of baseline models, so they are more popular with academia. On the other hand, there are many simple and easy to use frameworks, such as YOLO v5, YOLO v6, YOLO X, and Detectron 2. They focus on real-time detection and efficiency, and only provide 3 to 5 models with different sizes usually. In addition, they provide thorough deployment tools, so they are more popular in the industry. As we can see, when using these existing frameworks in practice, there still are several disadvantages. Number one, they often lack flexibility in terms of model sizes, so it's hard to apply them to different scenarios with different computation powers. For example, the YOLO series mentioned above only provide 3 to 5 models of 10 to 100 G-flops, so it's hard to cover various devices. Number two, they really have weak multi-scale detection capabilities, especially for small objects. It makes their application scenarios very limited. For example, object detection for drones requires higher performance on small objects, which does not accept detection methods with poor detection capability on them. Number three, their MAP latency curves are not good enough. So when they want faster models, they would get models with a much worse performance at the same time. It makes these models hard to satisfy real-time scenarios. To address these problems, we design and propose DAMO-YOLO. We focus on industrial landing and combine the advanced technologies of our team with it. Compared with other detection frameworks, there are three obvious advantages of DAMO-YOLO. Number one, we combine the NAS research results of our team with DAMO-YOLO to get low-cost customizable models with different sizes, which helps users to make full use of computing powers of devices. Number two, combined with the efficient wrap GFPN and the heavy neck paradigm proposed by our team, DAMO-YOLO has excellent multi-scale detection capability, which brings a wide range of applications. Number three, we propose a general knowledge distillation method on models of all sizes to improve the performance of the whole series of models without any loss. So, what practical values could these three technological advantages of DAMO-YOLO bring? First of all, it's the ability to get low-cost customizable models of DAMO-YOLO. The core is the MAE-NAS algorithm proposed by our team. It is a zero-shot NAS method, which means it can evaluate the performance of a model without training. So the search process is very fast and low cost. MAE-NAS supports architecture search with flops and latency as the search budgets, both of which are very meaningful for practical applications. Searching with flops as a budget outputs models that can make full use of the computing power of chips. And searching with the inference latency as a budget outputs models that are suitable for various real-time scenarios, which is very useful. Due to the large latency differences of an operator between different devices, we provide a latency database construction scheme for different chips. The figure in the lower right corner shows how to use MAE-NAS with latency as a budget to search for the optimal model. First, we construct the latency database by sampling and profiling the latency of different operators based on the target hardware device. Then, during the search process, we estimate the latency of the whole model using the latency database. While new models are searched and updated, only the models that are satisfied with the latency budget would be added to the candidate set. Otherwise, they will be dropped. Finally, after specific iterations, MAE-NAS will output the best model under the current latency budget constraint. The range of applications is an important indicator to measure the quality of a model, which depends on its multi-scale detection capability. Here we will show how we improve the multi-scale detection capability of our models. Two of the core technologies are efficient wrap GFPN and heavy neck paradigm proposed by our team. Efficient wrap GFPN is modified from GFPN, a previous work proposed by our team on iClear 2022. And so-called heavy neck paradigm means we assign most flops of models to feature fusion layers. As the flops ratios of different models in this figure show, the flops of feature fusion layers, which is also known as NEC of DAMO-YOLO S, make up nearly half of the flops of the whole model. This is different from other models whose flops are mostly assigned to their backbones. In the later sections, we will show the detailed analysis and experimental results to prove that our efficient wrap GFPN and heavy neck paradigm improve the multi-scale detection capability significantly. The third value is the distillation method of DAMO-YOLO. Model distillation or knowledge distillation is a method to transfer knowledge from larger models to smaller models to improve the performance of small models without extra inference cost. It looks like a powerful tool to improve the detection performance of models. However,
Studies on the distillation of single-stage detectors, such as the YOLO series, are relatively rare both in academia and in industry, and most of them focus on distillation on large models instead of small ones, such as FGD and YOLO V6. We think distillation on small models is much more meaningful in practical applications. Therefore, we provide a general distillation scheme on models of all sizes in DAMO-YOLO. This method not only improves performance significantly on models of all sizes, but also shows higher robustness. It requires no parameter tuning by using dynamic loss weights. There is another surprising fact that after we combine feature-based distillation, unbiased batch norm, and align module, it minimizes the influence caused by the bias of models to make it robust to heterogeneous models as well. It means a lot for the ability to generate low-cost customizable models we mentioned before. Based on these technology values of DAMO-YOLO, here we show the application values they could bring. In the figure on the left, we show the performance comparison between DAMO-YOLO and other state-of-the-art detection frameworks. The abscissa is the latency of models, and the ordinate is the detection result MAP on the COCO dataset. Of course, the closer the latency MAP curve is to the upper left corner of this figure, the faster and the better the corresponding framework is. Compared with other frameworks under the same MAP, the speed of DAMO-YOLO is increased by 20 to 40%. The flops are decreased by 15 to 50%, and the number of parameters is decreased by 6 to 50%. Besides, according to the table in the lower right corner, DAMO-YOLO outperforms all YOLO series on small, medium, and large sizes in both accuracy and speed. After this quantitative analysis, we can summarize the application values of DAMO-YOLO. First, DAMO-YOLO is fast and has fewer flops, so we can save computing power efficiently. Second, we can customize models for flops and latency constraints to improve the utilization of hardware devices. Besides, DAMO-YOLO is available on the ModelScope platform. You can use DAMO-YOLO in your detection tasks in 4 or 5 lines of code, so it's very easy to use. In addition to ModelScope, the code and the technical report are released to GitHub and archived respectively. Through the comparison and analysis before, we believe that you have realized the technology value and application value of DAMO-YOLO. Next, we will introduce these 3 advantages of DAMO-YOLO in detail from a technical point of view. We will dive into the implementation of DAMO-YOLO to help you better understand and use DAMO-YOLO. First, we will introduce the core technology to provide low-cost customizable models, MAE-NAS. This work was accepted by ICML 2022. The idea of MAE-NAS is very simple. We can formulate a deep network as an information system endowed with a continuous state space. And the goal of MAE-NAS is to find a network architecture that maximizes its entropy. First of all, we abstract the topology of network F as graph G, whose vertex set V represents features of this network and edge set E represents operators in this network. Based on this abstraction, we use HV and HE to denote the values endowed with each vertex and edge. So the set S defines the continuous state space of network F. Moreover, the entropy of set S measures the total information contained in this network or system F, among which the entropy of vertices measures the expressivity of the network, and the entropy of edges measures the complexity of the network. For the object detection task, we hope to maximize the feature expressivity of the network, so we only focus on the entropy of the vertex set. So, how do we calculate the entropy of features? As a matter of fact, according to the differential entropy of Gaussian distribution and the Gaussian entropy upper bound theorem, we can calculate the variance of feature maps to estimate the entropy, and get the Gaussian entropy upper bound when they obey the Gaussian distribution to approximate the expressivity of the network. Therefore, we can initialize all parameters of the backbone and the noise image by the standard Gaussian distribution. The noise image is fed into the network and it generates several feature maps. We calculate the single-scale Gaussian upper bound entropy of each feature map and then calculate the multi-scale entropy by the weighted sum of single-scale entropies. The second item in the formula of single-scale entropy is a scaling coefficient to avoid overflow during the calculation. We can simply set it to the L2 norm of feature maps. The weights alpha in the formula of multi-scale entropy is used to balance the expressivity of different scale features. They are obtained from experiments as the prior. In DAMO-YOLO, the weights are set to 0, 0, 1, 1, 6. We set the weights of the previous two layers to 0 because only the outputs of the last three layers are sent to the NAC. Based on these core ideas, we use multi-scale entropy as the performance proxy and use the evolutionary algorithm to search for optimal architectures. All these components make up MANAS. There are several advantages of MANAS. First of all, it supports various search budgets, such as flops, number of parameters, latency, number of layers, and so on. Second, it supports fine-grained mutations, including kernel size, width, depth, block type, and so on. So it's highly scalable. We provide an official tutorial to show how to add your block types easily to get customized search space and searched architectures. The link to the tutorial is placed at the bottom of this page. Last but the most important, MANAS is a zero-shot and GPU-free NAS method, which means the search process requires no data and no GPU. It only takes tens of minutes on CPUs to search for the optimal architectures, while most previous NAS methods need hundreds of hours to search on a single GPU. So the speed advantage of ME-NAS is obvious. Researchers could run more experiments in the same amount of time to meet their search demands using ME-NAS. Back to DAMO-YOLO, we use latency on NVIDIA T4 GPU as the search budget of ME-NAS to search models with different sizes for the goal of real-time applications. Based on the searched basic structures, we wrap them to backbones with better performance with structure wrappers. We provide two kinds of wrappers, ResNet style and CSPNet style. Experimental results show that the ResNet style wrapper makes smaller models more accurate and faster, and larger models with deeper depth benefit from the CSPNet style wrapper. MANAS has been integrated into our TinyNAS toolbox, and the TinyNAS toolbox is available on ModelScope now. On the TinyNAS page, after selecting the Detection tab, you can search for your architectures in tens of minutes by configuring using Web UI. At the same time, ME-NAS has been released on GitHub. If you are interested in ME-NAS, you can search your networks with more configurable arguments based on our codes. Next, we will introduce how DAMO-YOLO improves the multi-scale detection capability. Multi-scale detection capability depends on multi-scale feature fusion. In previous detection methods, the depth dimensions of features with different scales are very different. Our team proposed the GFPN on iClear 2022. It processes high-level semantic and low-level spatial information at the same priority, so it's beneficial to multi-scale feature fusion. The figure on the left shows the structure of GFPN, which looks complicated due to the complex connections. But after we understand the two design principles of GFPN, we will know what it is actually. These two principles are log2n link and queen fusion. To make GFPN deeper, we add skip layers after the fusion nodes and use log2n link to reuse features. Under the same flops and compared to the dense link, Log2N link makes JFPM deeper. To strengthen the feature fusion between different skills, we propose Queen Fusion. Each node in Queen Fusion receives features not only from its neighbor levels, but also from the same level. So it converts feature fusion from a parallel style over feature resolutions to a serial structure like this figure shows. Although the feature reuse and unique connection design bring the performance improvement of models, they increase the inference latency due to the slow align operators for features of different resolutions and the serial structure during feature fusion. So it's hard to satisfy the real-time demand in practice. Therefore, GFPN is efficient in flops but inefficient in latency. To use GFPN to improve the multi-scale detection capability, we further analyze and optimize it. We summarize the reasons for inefficiency in the following points. Number one, features with different scales share the same number of channels. It leads to redundant features and inflexible network configurations. Number two, there are too many inefficient upsampling and downsampling operators to fuse features with different scales, which slows down the whole model considerably. Number three, GFPN increases the depth by stacking lots of nodes. Due to the serial structure in Queen Fusion, when we add more fusion nodes, the length of the fusion path is increased significantly, which makes the parallelism of the model less efficient. To address these problems, we optimize GFPN on topology and fusion method and propose efficient wrap GFPN. First, in terms of topology optimization, we use different numbers of channels in features of different scales in efficient wrap GFPM, so we can control the expressivity of both high-level and low-level features flexibly under lightweight computational load constraints. The table on the lower left shows the depth and width analysis experimental results of efficient wrap GFPM, which indicates that features of different scales with different width make the model perform best. Besides, we performed the connection efficiency analysis of Queen Fusion. We found that the latency cost of upsampling operators is relatively high, but the performance improvement they bring is relatively small and much smaller than what downsampling operators bring. Therefore, we remove extra upsampling connections in Queen Fusion. In terms of fusion optimization, we fix the number of fusion nodes in efficient wrap-GFPN and use the well-designed fusion block to fuse features, which could avoid the low parallel efficiency caused by stacked nodes. Meanwhile, we introduce CSP connections, reparameterization mechanism, and the efficient layer aggregation network to further enhance the fusion effect. The table on the lower right shows the experimental results. As the table shows, adding CSP connections improves performance significantly with fewer flops. Reparameterization and ELAM also bring obvious performance improvement in the case of a small increase in latency. The head is also an important component in detection models. It takes the output features of the neck as inputs and outputs the classification and regression results. We designed an experiment to analyze the trade-off between efficient wrap-GFPN and head. The results show that under the specific latency constraint, the deeper the efficient wrap-GFPN is, the better performance the model achieves. Hence, we assign most of the flops to the neck to stack more fusion blocks, and only keep a linear projection layer in the head for classification and regression. We name the head with only one layer as zero head, and the design paradigm to assign most flops to the neck as heavy neck paradigm. The overall structure of DAMO-YOLO is shown in the figure below. It consists of the backbone searched by MENAS, efficient wrap-GFPN, and zero head. Finally, we will introduce knowledge distillation in DAMO-YOLO. The overall distillation strategy is shown in the figure below.
We distill the knowledge in the output features of efficient RepGFPN. Features of the student models are aligned with features of the teacher models by the align module, which is a linear projection layer. After alignment, to remove the bias of the model itself, features are regularized by the unbiased batch norm and then used to calculate the CWD loss of distillation. During the distillation process, we find that the weight of distillation loss has a large impact on the final performance. Excessively large distillation loss hinders the convergence of the student model. So we use the dynamic distillation weight, which decays as the training process. It's robust to all tiny, small, and medium models. All of them make up our distillation method, which is parameter tuning free and works well on models of all sizes. The distillation chain of DAMO-YOLO is L to M, M to S, and S to T. Among these models with different sizes, it's worth mentioning that although the backbone of the medium model is wrapped in CSPNet style, and the backbone of the small model is wrapped in ResNet style, distillation from the medium model to the small model brings stable improvement of 1.2%. It declares that our distillation method is robust to heterogeneous models. The final performance of distillation is shown in the table on the upper right. We can see that models of all sizes achieve better performance with stable improvements of about 1.2% after distillation. Let's summarize the implementation of DAMO-YOLO. Our MAE NAS supports searching for low-cost customizable models to make full use of computing powers of chips. Efficient RepGFPN and heavy neck paradigm bring powerful multi-scale detection capability. We also provide a parameter tuning-free distillation method that works well on models of all sizes and heterogeneous models to further improve the detection performance. DAMO-YOLO is available on ModelScope now. Codes and the technical report are released on GitHub and archive respectively as well. Welcome to try DAMO-YOLO. DAMO-YOLO is a newborn object detection framework, so it still has a lot to improve and optimize. We are working on more features, such as small object detection for drones and rotated object detection. We will release more models of different sizes, such as nano models for the edge devices and large models for the cloud devices. And we will release more exciting practical application examples in the industry. In conclusion, DAMO-YOLO will be long-term support and updated continuously by our team. We hope you can keep paying attention and give your feedback. Okay, thanks for listening. This introduction ends here, and one last advertisement. We are recruiting research interns, so if you are interested in object detection, quantization, or NAS, just send your resume to this email or contact us directly by scanning the QR codes in the lower left corner of this page. And if you have any issues or questions on DAMO-YOLO, you can comment below or discuss with us in the issue area of DAMO-YOLO on GitHub. Thanks.